take a look at these standard lithium-ion batteries. Every device you own relies on them, and they all suffer from the exact same physical bottleneck. To store and release power, they depend on a chemical reaction, specifically the physical movement of ions traveling across the cell. Because that movement requires physical space and time, the math is unforgiving. On this chart, there is a strict linear relationship between capacity and speed. To store more energy, you build a larger battery, and it will take longer to charge. But if we bypass chemistry and build a battery at the quantum level, the rules of scaling are entirely inverted. Suddenly, increasing the size of the battery doesn't slow down the charging process, it accelerates it. The larger a quantum battery gets, the faster it charges. This happens through superabsorption, where molecules enter a synchronized state and capture light collectively. It is a process that directly defies the limits of classical thermodynamics. For years, superabsorption existed strictly as a mathematical theory. Then, in 2022, a team led by Australia's National Science Agency, CSIRO, built a physical prototype. Here is how they set up the experiment. They built a microcavity, essentially a tiny, highly reflective chamber, and filled it with a photosensitive organic dye called Lumigen F orange. Then they fired an ultra-short laser pulse directly inside. The experiment worked. The dye molecules achieved superabsorption, acting as a single collective system to absorb the laser's energy simultaneously. But the team immediately ran into a barrier known as the super-radiance duality. In quantum systems, the same synchronization that allows molecules to absorb light instantly also forces them to emit light just as fast. The exact mechanism that allowed the molecules to charge at quantum speeds forced them to aggressively eject the energy right back out. The entire charge was lost in a matter of nanoseconds. The researchers built a battery capable of nonlinear charging speeds. Because it couldn't hold on to a single joule of power, it was practically useless. To make this technology functional, a combined team from CSIRO and RMIT University spent the next 3 years trying to engineer a trap. They needed a way to lock the energy in place without disrupting the fragile quantum state of the system. Their solution was not a massive freezing cryogenic chamber. Instead, they focused on a practical solid-state device that could operate at room temperature. Looking at this cross-section of the new architecture, you can see the breakthrough. Instead of a single chamber, they split the microcavity into 2 highly specialized stacked layers. The top section is the active layer. Its sole purpose is to trigger superabsorption, working like the 2022 experiment to capture the incoming light at quantum speeds. But before the energy can be ejected, it is immediately shunted downward into the adjacent storage layer. By physically separating the charging process from the storage process, the engineers created a way to work around the standard limits of quantum thermodynamics. That bottom storage layer is composed of molecular triplet states. A triplet state is a specific electron arrangement where the particles are paired in a way that restricts them from releasing energy through light emission. In quantum mechanics, this acts as a dark state. It functions like a one-way valve that refuses to emit light, blocking the rapid decay that ruined the first prototype. The lab data confirmed the theory. By utilizing this dark state, the battery's energy retention jumped by a factor of 1,000, extending its lifespan from nanoseconds to tens of microseconds. That window was long enough to extract the energy. The team successfully completed the first full quantum charge-discharge cycle, pulling a measurable, steady-state electrical current out of the device. This was the defining moment. A theoretical concept was finally successfully converted into physical, usable electricity. Now, a battery that lasts for 40 microseconds is not going to power an electric vehicle or a smartphone. But in the world of quantum computing, a microsecond is a long time. These massive gold cryogenic chandeliers are currently hitting a physical wall that this battery is uniquely suited to solve. Right now, executing logic in these processors requires energy from room temperature electronics outside the cooling chamber. Pumping that power in creates heat, which limits how many qubits, the computer's basic processing units, can be packed into a single machine. By embedding a quantum battery directly into the computer, researchers can create an internal loop where energy is recycled. This significantly reduces the heat signature of the processing gates. moving the system towards the thermodynamic limit, where logic can be performed with zero heat dissipation. Cutting those external shower lines and heat loads could allow researchers to quadruple the number of qubits they integrate within the exact same physical space. Beyond computing, this architecture can be applied to solar technology. Because superabsorption is driven by collective light capture, it could allow solar cells to harvest energy in low-light environments where traditional panels are inefficient. The engineering hurdle now is volume. To provide off-grid power for commercial electronics, researchers must scale these devices up from millions of molecules to billions. The fundamental theoretical barrier that once made quantum energy storage a mathematical ghost has been dismantled. While large-scale applications are still in the engineering phase, the core physics of room temperature superabsorption are now proven. By trapping light inside a molecular dark state, we've moved past the chemical limits of standard batteries. We now have a blueprint for a future where energy is captured and stored at the speed of light.